This is question number 4 on the circuits review packet. The first question has 3 identical resistors, each with resistance R, capacitor 1, microfarad, actually nanofarad, and it's connected to a 30-volt battery with negligible internal resistance. In the first case, switch 3 is open and switches 1 and 2 are shut. I think it's easiest to deal with this problem by just treating each resistor as having a value of 1 ohm. If you do that, then solve for the equivalent resistor resistance of the parallel portion of the circuit, these two guys, you end up getting 1 over that equivalent resistance is equal to 1 over R plus 1 over R, which is of course 1 over 1 plus 1 over 1. That gives you 2 over 1 with an equivalent resistance of 1/2 of an ohm. So when you then find the total resistance, we would then say, well, let's add the equivalent resistance, which is in series with our initial resistor, or our first resistor up here, R, and I end up getting 3/2 of an ohm, or 1.5 ohms. Solving for the total current using Ohm's law, this is going to be voltage over resistance, and I'm going to get my 30 volts over 1.5 ohms, and I end up getting 20 amps. So the current flowing out of the battery and through this first portion of the network until it gets to that node is 20 amps. And if that first resistor R is 1 ohm, then again, using Ohm's law, V equals IR, I can say that the voltage dropped across that first resistor R1 is the total current times the resistance value R1, and I'm going to get 20 amps times 1 ohm, or 20 volts. So I got a 20 volt drop across resistor 1 when comparing one side to the other side, and that's what this voltmeter here is going to read. Alright, let's move on. Now it says switches S1 and S2 are now open. So these guys are opened, and that means then once I close switch S3, I basically have a series circuit with 1 resistor and 1 capacitor in it. They say that the switch has been closed for a long time, so we can then assume that the circuit is at steady state. Initially, we are going to have a voltage drop across this resistor. As a matter of fact, the instant that we shut the switches, we still have a voltage drop of 20 volts across that resistor, but then that starts to go down, and the reason is this. Charge starts to build up on the upper plate here of that capacitor, and when we reach steady state, I've got 30 volts across that capacitor here, and therefore no more charge is going to flow in the circuit. There's going to be nothing dropped across resistor R1. There's going to be no current in the circuit when I'm at steady state. Another way of considering this is that this is a simple loop with a break in it, an open in it. This capacitor is effectively an open to this DC EMF, this DC source. So the voltage dropped across the capacitor is going to be this 30 volts. I've got basically on this green line here, if you will, I've got 30 volts of potential all the way up into that upper plate. And on the red plate beneath it here, I've got 0 volts. That's connected electrically to the anode of the battery. So I've got a 30 volt difference in potential across there. I've got a known capacitance of 1 nanofarad. Solving for the charge on the capacitor, it's simply going to be V times C, or the 30 volts times the 1 nanofarad of capacitance, and that's going to give me 30 nanocoulombs of charge. So that's the charge across the capacitor when I've opened the switches S1 and S2, and I have closed the switch S3. Let's go ahead and move on in this problem. It says after the capacitor is fully charged, the switches S1 and S2 remain open, switch 3 remains closed, and the plates are held fixed. And then they take this conducting copper block and it's inserted midway between the plates as shown in the sketch below. The plates of the capacitor are separated by the distance of 1 millimeter, so they give you some geometry here. So they want to know first, what is the potential difference between the plates? So in this first question, you can say that the difference between the plates hasn't changed. I still have 30 volts dropped across this capacitor between the upper plate and the lower plate. Nothing has changed. So the answer is quite simple. Simply 30 volts is still the electric potential difference between the plates. What is the electric field inside the copper block? This is a conceptual question. The copper block is a conducting copper block, so therefore this is like asking what the difference in potential is across an ideal piece of wire. So here's a piece of copper wire. What's the difference in potential if this is my voltmeter between these two different points? It should be 0, and the reason is it's conducting. So I can't have a difference in potential between two different pieces of a conductor. And for that reason, if I define electric field by the difference in potential over the distance between those two differences in potential, if I've got no difference in potential, I can say that the electric field is going to be 0. There is no electric field, and for that matter, there's never an electric field inside a conductor. On the diagram above, they want you to show arrows showing here the direction of the field. So the upper plate is positive. Notice that's going to induce a charge here in the copper. So I'll get some negative charges being attracted by the positive charges there, and the positive charges will be repelled in this copper, so they'll kind of align here on the bottom. Of course, I've still got the relative negative here on the bottom plate of the capacitor. So I get effectively two different electric fields, two different capacitors. I've got an air gap capacitor on the top. I could call that C1, if you will, and I've got another capacitor on the bottom. So here's my electric field on the top, and I've got another electric field here that I'm denoting by these blue lines directed downward. This is, of course, the direction of a force on a positive test charge should one be placed inside the field. So that's part 3. Part 4, they want to determine the magnitude of the electric field in each of the spaces between the plates of the copper block. A couple of different ways of approaching this. You should recognize that if I were to draw a dashed line right down the middle of this guy, that I would have, if I have 30 volts of potential on one plate and 0 volts on the other, the potential varies uniformly here. So I'm going to have 15 volts is going to be the electric potential here on one of those plates. So my difference in potential, if I consider the upper capacitor to be, let's call it capacitor number 1, I've got a difference in potential of 15 volts. That's the key to answering this, because the rest of it is pretty simple. The distance, or the gap, is now 0.25 millimeters. I can discern that from the geometry here that they've given me. So I've got 1 millimeter between the plates. I've got a ½ millimeter thickness for this copper block. So therefore, the distance between the plates of each of the individual capacitors is 0.25 millimeters. Electric field by definition, as we saw up here in part B, is simply the difference in electric potential over the distance between them, and so I'm going to get 15 volts over that distance of 0.25 millimeters, or I can say 0.25 times 10 to the -3 meters. So electric field volts per meter would be appropriate units, and so I end up getting 60,000 volts per meter being the magnitude of the electric field between one of the plates and the copper block.